Chapter 19, Part 2, Cardiac Physiology, Screencast 1. Now, we are moving on to cardiac physiology, and the first part that we will be addressing is the electrical aspect of the heart. So one of the things I want you to keep in mind is this saying that you're going to hear from me, electrical first, mechanical second. Really what this is saying that there's no way that we can get a mechanical event such as cardiac contraction unless there's an electrical event that precedes this. If we're talking about skeletal muscle, we're looking at a motor neuron. One thing that makes cardiac muscle very different, it actually generates its own electrical activity. And a part of this is due to what we refer to as the intrinsic conduction system of the heart. Now, this is terminology that I want to put some emphasis on. When we use the term intrinsic, we really are referring to something that is an inherent characteristic of the tissue and built in, whereas extrinsic is something from outside. Examples of extrinsic that I will address in the future will be neurotransmitters, hormones, and medications. So when we are talking about the intrinsic conduction system, this is a system that is responsible for initiating and the conduction of electrical events to make sure that we have coordinated contraction. When we look at the cells that are involved here, we actually look at pacing or nodal cells. These are different from other cardiac muscle cells because they're responsible for generating an action potential, but they do not contract. When we look at the role of the autonomic nervous system, it influences the activity of the heart. Remember, it is not going to be responsible for generating the electrical activity. This is done by the heart itself. Now, when we look at the conduction system, it's made up of a number of different structures. They are the SA, or sinoatrial node. This is considered to be the pacemaker. When we talk about normal sinus rhythm, what we are saying that this is where it originates, that the electrical signal is originating from the SA node. We then have the AV, or atrioventricular node. Note from the diagram, there's no real physical connection here. This is important. So this kind of indicates there's going to be what we refer to as an electrical delay. And one of the things that I will put an emphasis on is making sure that there's adequate time for the ventricles to fill. And we'll address this later on. From this point forward, everything is connected, so things will move very rapidly. We have the AV bundle, formerly known as the bundle of His. This will break into bundle branches, right and left, and then we'll have Purkinje fibers, which will be running through the walls of the ventricles. Now, within the cardiovascular control center, within the medulla oblongata, we're going to have two areas that are really critical. They are the cardioacceleratory and the cardioinhibitory centers. This is where we're going to be getting signals from various receptors that are going to respond by either increasing sympathetic or parasympathetic activity. Now, keep in mind, we're talking about the role of the autonomic nervous system with respect to modifying cardiac activity, so it influences and does not start or is responsible for electrical activity or contraction of the heart. Now, this is a very important diagram, and I want to make sure that we address the differences between what parts of the heart are innervated by parasympathetic activity versus sympathetic activity. Now, when we look at the input can come from a number of various receptors. There are going to be baroreceptors, chemoreceptors, and so on. But what I want to put the emphasis on here is let's look at where the output is going. And I first want to put an emphasis on the sympathetic activity. And when we look at where we have the sympathetic activity of the heart, what I want to make sure that we understand here is we have sympathetic activity going to two areas of the heart. One will be the pacing center, so the SA node and the AV node, but we are also going to notice that there is sympathetic activity primarily to the myocardium also. This is going to be important because when we talk about cardiac output is determined by stroke volume and heart rate, so both of those parameters are actually controlled by the sympathetic nervous system. When we look at the parasympathetic nervous system, we see that it only innervates one part of the heart, and those are the pacing centers. So the only aspect of cardiac function that parasympathetic activity has direct impact on is going to be heart rate. It will decrease heart rate. Parasympathetic activity has no direct impact on contractility or stroke volume. This is really important. Now, when we look at how the heart is actually stimulated, there's going to be two events here that play a role with respect to the contraction. We have the conduction system. So this is responsible for the initiation and propagation of action potentials. Then we have the cardiac muscle cells, which will initiate action potentials and contract. This originally happens first in the atria and then the ventricle. So keep in mind we have a very coordinated electrical activity, but that should not be surprised when we look at how coordinated contraction is. The atria must contract prior to the ventricles. Now here we're looking at a couple of things in particular. We're looking at both the conduction system and cardiac muscle. So when we look at the conduction system, keep in mind we're talking about originating from the SA node. We can see that here. So remember, this is the source of the initiation of action potentials. And what we're going to notice here through the conduction system is the spread of action potentials and propagation throughout the atria and the conduction system. Now we're actually looking at the contractile or cardiac muscle cells. So now we're looking at the propagation of the action potential. This happens along the sarcolemma of cardiac muscle cells, and this is going to result in the contractile activity or contraction of cardiac muscle. Now, remember what we talked about previously. Cardiac muscle is striating just like skeletal muscle, so we're looking at the sarcomere as being the functional unit of contraction. So everything that have an impact on the contraction of skeletal muscle carries over to cardiac muscle since the architecture is similar. So this means cross-break cycling, sliding filament model, all of those are playing a role here when we're talking about cardiac function. Now, here, the first thing that we're looking at is a sinoatrial nodal cell, or I will refer to them as a pacing cell, and this is at rest. Now, a couple of things that I want to point out here. One, we're looking at what is being referred to as a resting membrane potential. I am going to refer to this as a false rest, and we will see why I use that terminology. Here, we're looking at negative 60 millivolts. And if we kind of go back to using a neuron as a frame of reference, the resting potential for a neuron is negative 70 millivolts. So this is not as negative. This will be important when we compare it to the resting membrane potential of a contractile cell. Now, the other thing that we see in this diagram are three different voltage-gated channels. And this is indicating what ions are going to be involved in the generation of action potentials in a pacing cell. So we're going to have voltage-gated cation channels. So we are going to refer to these as slow voltage-gated sodium channels. We're going to have fast voltage-gated calcium channels. And then we're also going to have voltage-gated potassium channels. So the three ions that are playing a role here are sodium, calcium, and potassium. So let's take a look. Now, one thing that I want to make sure that you're comfortable with, we are not using numbers to refer to phases of the initiation of action potentials. We're going to talk about reaching threshold, depolarization, and repolarization. So let's look at where we are. So we have a resting membrane potential of negative 60, but remember, I've referred to this as a false resting membrane potential, and I hope that you can see why I use that term right now. Here we get to negative 60, but there is no rest there. We spend no time. Now, this first part is reaching threshold. Threshold is about negative 40 millivolts, and getting to threshold is going to be achieved by sodium moving in through slow voltage gated channels. So now we're actually going to get to that threshold. Once threshold occurs, we now hit depolarization. This is going to be a significant difference than what we refer to as our reference point with respect to the neuron. The neuron depolarization is due to the influx of sodium into the cell. Here, note what is responsible for depolarization. It is the inflow of calcium. You'll also notice that the change in membrane potential is not as dramatic as what you saw in a neuron. We get to the point where we reach peak, and then at this point, we're going to begin repolarization. And repolarization will be due to the outflow of potassium. And so this will bring back to that false resting membrane potential, and then the whole process will start over again. Now, when we look a couple of things, one SA node action potential starts about 0.8 seconds after the last. So remember, there's one action potential per mechanical event. So if we look at what this translates as 75 action potentials per minute, but remember, there will be a mechanical event associated with each electrical event running into 75 heartbeats per minute at rest. Now, one thing to keep in mind here is there is something known as parasympathetic tone. Remember, parasympathetic nervous system is predominant at rest, and also remember that the only impact that the parasympathetic nervous system is on heart rate. So typically what we see, because of this vagal tone, we are actually going to see a slower heart rate. If there was no vagal tone, we would probably look at seeing the SA node firing at about 100 action potentials per minute, which would result in a resting heart rate of approximately 100 per minute. What we see is much lower than that, and it is due to vagal tone or parasympathetic activity, which is keeping it much lower. Now, I like these diagrams, and I want to kind of walk through what's happening here. And so what we're looking at are the channels that are involved, but remember, the electrical events are caused by the movement of ions. So when we are reaching threshold, notice the only channels that are open are the slow voltage gated sodium channels. This results in sodium going down its electrical chemical gradient and basically just moving into the cell. This is going to be responsible for bringing the cell to threshold, or approximate -40 millivolts. At this point, we are going to see those slow voltage gated sodium channels closing. So now let's look at depolarization. The only channels that are open here are the fast voltage gated calcium channels. The sodium channels and potassium channels are closed. So what's going to be responsible for depolarization at this point is the inflow of calcium coming in. Then the calcium channels will close and we'll begin the repolarization phase. And this is going to be due to the outflow of potassium. Repolarization is always going to be due to the outflow of potassium. And this is going to bring us back to that false resting membrane potential of approximately -60 millivolts. Now, here what we're putting into effect is the initiation and spread of the action potential through the cardiac system. First, we're looking at the SA node and atrial myocardium. The action potential is generated at the SA node. The action potential will spread via gap junctions between cardiac muscle cells throughout the atria and make its way to the AV or atrioventricular node. Now, notice there isn't really a physical connection between the SA node and the AV node. So what we're going to notice is a little bit of a delay or hang up at the atrioventricular node before it moves on to the AV bundle. This is important because this is going to slow things down a little bit. And one thing I'm going to put an emphasis on is making sure that there's adequate time for the ventricles to fill. This also is going to ensure that the atria contract simultaneously before the ventricles. Now, when we look at the AV bundle, we're going to look at the conduction to the left and right bundle branches and then to the Purkinje fibers. From the Purkinje fibers, the action potential is spread through gap junctions between cardiac muscle cells throughout the ventricles. Now, when we look at some specialized features that are associated with the ventricles, we have to keep a couple of things in mind. One, the Purkinje fibers are relatively large in diameter than other cardiac fibers. Go back when you were in 144 and talked about factors that impacted conduction velocity. One was myelin. That is not going to play a role here, but the other was a wide diameter axon. So when we look at Purkinje fibers, they have a much larger diameter, so the action potential will move very rapidly through the Purkinje fibers. This is going to make sure that the ventricles will contract at the same time. Then we're going to see the papillary muscles. They're going to immediately contract, and we're going to see basically the papillary muscles. They anchor the chordae tendineae, and they're going to pull on the cusps just prior to increase in pressure within the ventricles. We're also going to notice that the stimulation begins at the apex or the inferior portion of the heart, and this is going to guarantee that we have enough contractile force that blood is going to be effectively ejected toward the arterial trunks. Now, there are some terms that we want to kind of take a look at, and the clinical view that we are discussing here is an ectopic pacemaker. Now, what an ectopic pacemaker is, something other than the SA node is generating the electrical activity. Now, there are other cells than the SA node that have the ability to spontaneously depolarize, but we will see that they depolarize at a rate significantly slower than the sinoatrial node. Now, if for some reason there is a problem with the SA node, we're going to look at the AV node coming in and act as the default pacemaker. So there is a backup system. But the problem here is the AV node has an inherent rhythm of 40 to 50 action potentials per minute or 40 to 50 beats per minute, and this is plenty to sustain life. Now, other tissues, such as cardiac muscle, can only generate action potentials at a rate of 20 to 40 action potentials per minute, resulting in 20 to 40 beats per minute. And typically, this is not fast enough to sustain life. It really is much too slow.